So good morning and welcome to the second session of Nonlinear Structural Mechanics with Python workshop. So the plan for today is we'll continue where we left last time. We'll look at more programming practice problems in Python. Then we'll look at coding the assembly of the global stiffness matrix, again using Python. So once these two are done, you will be able to solve the solution to a bar problem, right? We'll try to solve a simple bar problem using Python. And then we'll look at beams. So we look at beams in a plane. We'll look at this stiffness matrix. We'll derive the stiffness matrix, and we'll also solve a couple of problems on beam solutions. So I hope you had the chance to go through the PDF and were you able to code the matrix multiplication exercise that I said yesterday? So matrix vector, we given a matrix and a vector, were you able to code it last time?
Yes, sir.
Okay, good. So that's a good starting point. So we can go to the codes and then open C1 Python basics. Right, you can open that. Sorry. So open this and click Google Collaboratory. Right. So it will open in a coding screen. And you can put the mode in this split screen, so that you can see my window as well as your window together. So put it in split screen. Okay, I'll put it in full screen because if you put it in split screen, you will be able to see only half of it. I'll put it in full screen so that it is clearly visible. So you might last time we saw the basic arithmetic operations. So this is just to look at what basic things Python can do. Then we looked at loops in Python. So yeah, so in the loops we saw first thing was this was given as an example. Then we did a sum to the first n squares, right? So sum of first n squares, the squares of first n natural numbers. Then we had a small exercise on matrix multiplication. So by now you might be comfortable with the basic syntax of Python. It's way easier than C or any of the classical low-level languages, so it's easy to work with. Then you can also look at certain libraries. So one library that we'll be using repeatedly is the Python NumPy library, which is useful for manipulating matrices and vectors. So you can look at this. So the NumPy library is imported as, just type import NumPy as whatever name you want. You can also import it directly as NumPy. So one thing with Python is just like how you include hash include in your C codes, you need to include libraries that have certain functions. So say you have this array. So this is a list, right? So you have a list of numbers. List of numbers, list in Python can be anything, list of anything. So you can have a list, you can define a list. A1 is equal to, you can define a list of, say the string A, the string ball, then you can have 2.35. Then you can also have an array, you can also have a list inside a list. So you can have something like 2.3 to 0. This is also a list. So a list in Python is a very general data structure. So you can put anything in a list. So suppose if I say print A1, this will come later, right? So this we can come later. it's just connecting. We'll see. Okay. Now it is evaluating it. So yeah. So A1 is a list of different entities. You can have an array, you can have a number, you can have a string, you can have a character. And Python lists handle general entities like this. But the problem is you cannot add two lists. Even if two lists are just of numbers, it's not possible to add them. So what this library offers is we can treat lists as matrices. So suppose I have a list A and I have another list B, say 2, 0, -2, 4, and -6. Now, if I want to add these two, then I can convert them to NumPy arrays. So in order to convert to in order to convert it to NumPy arrays, you just use this A is equal to np.array of the list. So take this array A and you want to convert it to a vector on which you can do operations such as addition, matrix multiplication, etc. So if you want to do that, we convert it to a NumPy array. So, and you convert B also to a NumPy array, np.array B. Now, if you want to see, say, A plus B, you can do it directly. But as long as it is not a NumPy array, you cannot do the addition. So if I run this piece of code, yeah, so you get the sum 3 minus 1, 0, 9, and 1. Now, what else? Yeah, so this is a basic operation, right? This is a basic operation. You can also print A minus B. So you can print A plus B, you can print A minus B, right? You can print A star B. So A star B is element-wise multiplication. So it is not, so basically you can't do a matrix multiplication of A and B because they are, the number of columns in A is not the same as the number of rows in B. So you cannot do a matrix multiplication as A star B. So what this returns is if the two arrays are of equal length, it will return element wise. So it will take first element of A, multiply with the first element of B. Second element of A, multiply with the second element of B, and so on. So A star B will actually return, it's like in this case, return 2, 0, -420, and -42. So, these are some basic operations. So similarly, you can also define A divided by B. Now here it's not possible. You have a division by 0, so we can't do it. But say B divided by A, that can also be returned. Right? You can return. So all these operations, plus, minus, star, division, and maybe even power, these are all defined element wise. So take every element of A and do this operation with the corresponding element in B. Okay, so this is just a basic thing. Then if you want to access an element of a array, right, use the square brackets, right? So if you want to take the first element of A or something. So numbering starts from 0. Remember that numbering in Python starts from 0, not 1, unlike MATLAB or any other languages. It is similar to C. So if you are comfortable with C, even in Python, the numbering starts with 0. So the first entry is A of 0. The fourth entry is A of 3. So in this case, if you have to print A of 0 and A of 3, we should get 1 and 5. Let me also print some A of 2. Right, and maybe I'll make it A of 3 plus B of 2. So what should I get? A of 0 is 1. A of 2 is 2. A of 3 plus B of 2 is 3. So it has to return 1, 2, and 3. Right? So this is how you access a certain particular entry of an array. Then matrices, as we did yesterday, they are just two-dimensional lists. So you have a list which is composed of different lists. So every list of the matrix you can treat as every list of this big array A every list in this big list A, you can treat it as a row of a matrix. So if you have this matrix, it is just a list of lists. So that is one way you can store a matrix, but you should make sure that every row has the same number of entries. Otherwise, it is no longer a matrix. It is some other weird data structure. So every row should have the same number of entries. Then you use this np.array of that. It converts it into an operatable matrix. So this is an operatable matrix. This is an operatable matrix. You can also define another matrix, same as a two-dimensional list. You call it as you define it as a list of lists. Then you can do all kinds of arithmetic operations on the matrices. So if this is a 3x3 matrix, this is a 3x3 matrix. Dimensions should match exactly. Then if you sum them together, what should we get? We should get like 1 plus 2, 3, 2, 3, 4, 6, 6, and 7, 9, 12. So if you evaluate this, yeah, you get this. Yeah, for evaluating, either click this or you press Shift Enter. You write a code in this this gray box. Then if you want to evaluate it, just save your file, and then press Shift Enter. So this will be evaluated. Then you can also evaluate the difference. You'll get the difference. You can multiply a matrix by a scalar. Right, a scalar multiplication is possible. You can multiply it by something. So the scalar can be an integer. It can be fractional. It can be decimal. Doesn't matter. Again, the star between matrices returns a matrix with the corresponding entities multiplied. So A star B is a matrix with A of 0 multiplied with B of 0, A of 1 multiplied with B of 1, A of 2 multiplied by, and so on, right? A of 0, 0 multiplied by B of 0, 0, A of 1, 0, 1 multiplied by B of 0, 1, and A of 0, 2 multiplied by B of 0, 2. So it will multiply corresponding elements of the two matrices and put them in the right spots. So this is not matrix multiplication. Should be careful. This is really not matrix multiplication. So yeah, this you should be careful. Okay, I think I am editing the file that I just uploaded. So yeah, so maybe you can make a copy of this file just as you did yesterday. You can use the files that you have uploaded in your Google Drive yesterday. That will be better. Otherwise, if multiple people edit it, it's a problem, right? I should have made a copy, but I forgot to do it. Yeah. So you can define the transpose of a matrix. Just type np.transpose of A. You get the transpose of A. So these are the basic matrix operations. And finally, for matrix multiplication, you cannot do A star B. So in that case, you have to use the function dot. Right? If you want to multiply a matrix with a vector, say this is a 2x2 matrix, and this is a 2x1 vector. So the number of columns in A is equal to the number of rows in B. If you want to evaluate this, just use A dot B. So you get, so the first element has to be 0, 1 minus 1, 0. And the second element has to be 2 plus 1, 3. So you can evaluate it. You get it, right? And another thing, so if you want to access the, if you want to access the elements of a matrix, you can use the comma notation. So if I want to get the 2, 2 element of a matrix, right? So just say A of, in this case, numbering starts with 0. So you have to say 1, 1. Right? So the 2, 2 element of this matrix A is 1. And if you want to get the element in the first row, second column, so the first index has to be 0 because it is first row and numbering starts with 0. And the second column will be 1. So here it has to return -1. So this is how you access the elements of a matrix. Mostly we will not need anything beyond this. So from the NumPy library, most of the things in mechanics, in computational mechanics, structural mechanics, deal with matrices. We cannot live without matrices. So matrices are essential, and something that helps us handle these matrices easily in Python is the NumPy library. Now, you can also, so is this an invertible matrix? Is A an invertible matrix here?
Yes, sir.
Yes. Why? How do you say that?
Determinant is not 0, so it's invertible.
Okay, I couldn't hear you. Is it?
Determinant of this matrix is not equal to 0.
Yeah, the
So,
determinant is 3, so it is not 0, so it is invertible. And you can also do matrix inverse in this NumPy. So this is matrix inverse. And suppose I want to solve. So matrix inverse often happens when we want to solve equations such as Ax equal to b, right? So I can go to this notepad. I'll make a new page. So if you look at it carefully, the inverse of a matrix is useful. Inverse of a matrix is required for any scientific application. You require it only when you want to solve a system of equations. Otherwise, the inverse of a matrix is not really important. The inverse of a matrix is required for solving system of equations, system of linear algebraic equations. So when you have a system such as Ax is equal to b, it is to find x. If A is invertible, you say x is equal to some A inverse b. But do you actually need this matrix A inverse? It's not really required. So if you do Gaussian elimination or some other kind of solving technique, if you're able to solve for x, right, what is actually required is x. You don't really need to construct A inverse as a matrix and then multiply it with b. That has more number of computational operations than directly getting x. So you can get the inverse if it is required, but most often it is useless to construct a 3 cross 3 inverse of A, while you can get the 3 cross 1 end result directly. So you don't need to do it in 2 steps. So think about it. One way to solve this is use Gauss elimination and get to this point directly. Just Gauss elimination, or there are various kinds of solving. There are thousands of techniques to solve a linear system. So use one of them and directly get to the solution. The other thing is construct an inverse like this. So here you just have to uh, construct A inverse and then use A inverse to get x, right? Then multiply A inverse with x, right? So this is a two-step process, and in as an intermediate step, you have to construct a full 3 cross 3 matrix, which is not really required. You just directly get the solution that we want rather than constructing the inverse. So yeah, Gauss elimination will take you to an upper triangular matrix with you'll get an upper triangular matrix multiplying x equal to some c, right? So Gauss elimination will take you to this form. Then you do back substitution and get what x is. So this is way shorter than constructing a full matrix and multiplying it with multiply with b, not x. What I have done. Yeah, multiply with b and get x. So another thing is when you do inverse on a computer, is by elimination. Right? So this you have to remember. So computing the inverse of a matrix is always by elimination. It is not by. So if you have a 3x3 matrix or a small matrix on paper, what you do, you can say A inverse if it exists. It is 1 by determinant of A multiplying the adjoint of A or the cofactor of A transposed. Right, this is a high school formula that you might be remembering, but this will work. This will work always. But this formula is it's very expensive to implement on a computer. For example, if you just see how the determinant of A is evaluated, you see for a 2x2 matrix, if you have a matrix A, B, C, D, it is simply AD minus BC. If you take a 3x3 matrix, it is A EF minus F EI minus FH minus B DI minus FG plus C DH minus EG. Now suppose you have a 4x4 matrix. So here you have just one kind of you have two multiplications and one sum, right? One subtraction, that is just a sum, adding the negative. Here you have two multiplications and one sum for every element in the first row. So here it is 2m and 1s, which is done n number of times, right? Here you take one element in the first row and compute a 3x3 determinant. So here it will be n multiplying a 3x3 determinant, which itself involves n number of two multiplications and one sum. Now, if you have a 5x5, what happens? So 5x5 will have another n multiplying n multiplying n multiplying 2m 1s. So if you look at how the number of operations scale up, just take this 2m 1s as one unit. So a 2x2 matrix will have 2x2 when n is equal to 2. A 2x2 matrix will have just one unit of operation. Say one unit is two multiplications and one subtraction. If you have a 3x3 matrix, what happens? You have n units. And if you have a 4x4 matrix, you have n square units. Because for every element, you have to evaluate a 3D determinants. A 3x3 determinant. If you have n equal to 5, you have n cube units. Right? So for a general n, you have how many units of computational operation? You have n power n minus 2, right? Which is a very, very fast growing function. So if you have to evaluate, say, if you want to evaluate for, say, n equal to 10, for n equal to 10, what it is? It is 10 power 8 operations. And 10 power 8 is like 100 million. So this itself is, this is just gone. This will cripple the system. This you don't. And this is just a 10x10 matrix, remember. A 10x10 matrix is a very small matrix. When you look at real structural systems, which has got a real multi-story building, which has got thousands of beams, or you look at some analysis of a bolt, when you discretize with a large number of finite elements, the matrices that we typically get in a real finite element analysis have n of the order of 10 power. So it'll have way above 1 lakh degrees of freedom. So the number of degrees of freedom will be 1 lakh to 1 million. And imagine the cost of computing the determinant with such a large system. So it's basically not possible. So whenever you do an inverse or solution on a computer, it is always done by elimination. There's no other way. So this makes sense why you don't need to construct A inverse, because how do you get A inverse by the other method without using the determinant? You can use elimination, right? So you augment A with an identity matrix, and then you make a series of row operations so that you get an I here and A inverse here. So this process is costlier than solving AB, where you get IX. So here you have to eliminate only one column, whereas here you have to eliminate three n columns, and all those n columns are also not required. You only need to solve for X. So this is the reason you always, when you do things on a computer, you do directly to get the solution and not the inverse. You don't need to construct A inverse explicitly. So why did we do all this? So the reason I did all this is, if you want to get a matrix inverse, don't worry about constructing the inverse directly. So the only valid reason for needing the inverse of a matrix is to solve a linear system. So suppose let us look at a matrix. Let's say matrix. Let us say A is 1, or say a matrix for which. Okay, we'll do one thing. Let us have the same matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. And let me first choose X, right? Let me choose X as some 1.5, 2.5, 3.5. But this X has to be, yeah. So now so these are lists. A is a 2-dimensional list, X is a 1-dimensional list. Now I want to convert them into matrices on which I can do operations. So I'll do A is equal to np.array A. Yeah, I hope you're also doing it parallelly with me so that you can learn the things quickly. And X also you can convert it to a list. Sorry, a matrix X. But now if you convert X to a matrix, you'll get a row matrix. So I want the transpose of it. So let me do X as transpose of it. So it is np dot transpose of this matrix. Okay. Now let me construct the right hand side vector as the product of these two. So how do I do product? I told you, right? What is the function to do product? A matrix vector multiplication. How do you do it?
Dot.
Yeah, A dot X. So save it and run this piece. Okay, it is run. Now I'll say print A, X, and B. Okay, A is this, X is this. Why is X a row vector? It's okay. Don't worry about it. It is just displaying in this format. That is fine. And B is something like this. So B is this. Now let us solve. So if I solve for if I solve for this, I should recover X, right? So I can solve for AX equal to B. So that I do it as X is equal to A dot solve, sorry, NP dot linear algebra dot solve A comma B. Okay. It says singular matrix. Why is it singular? It is not singular, right? It is.
A is a singular matrix.
Oh, A is a singular matrix. Okay, then we can't do it. Let me make it -5 then. Okay, I didn't expect it to be singular, so yeah. Okay, now it is not somehow. Okay, for some reason 1, 2, 3, 4, 5, 6, 7, 8, 9 was. Oh yeah, if we add the first two, we get. We don't get, right? Yeah, for whatever reason it was singular, but now it is not singular. Okay, so now we are dealing with a non-singular matrix. So let me call this x1 and let me call it x2. Of course, if everything is done correctly, x1 should be equal to x2. So let us print x1 and x2. Okay, so they are same. So this shouldn't be surprising. I can also make this as p, and I can solve for x. Right? So I'm calling this as B. I'm having a matrix A. I'm just solving it. Now I don't know the solution, so I can just get the solution. So yeah, and another thing, if you have some things like this, 10 power minus 17, it is basically 0, because there is something called a machine epsilon. So small numbers, well they, so you know that numbers are represented by floating point representation in the computer, and in that process there is a slight error that is incurred. So numbers are not exactly represented in the floating point binary representation. So if something is 0, it can give such errors. So it can be something like 10 power minus 17. Whenever you get a value less than 10 power minus 15, treat it as 0. Right? When you get a value of when you're doing some computation and you get a value less than 10 power minus 15, it is basically 0. So this is actually 0. When you get a number of magnitude less than 10 power minus 15, that's actually 0. So the solution to this system is actually minus 2.5, 0, and minus 0.25, 0, and minus 0.5833.
Sir, it is x2 is A inverse multiplied by B. That one answer. X2.
Yeah. X2 is, we are solving for, so when you put np dot linear solve a comma b, it actually takes it solves for a x equal to b. So it is actually A inverse multiplied by B, but it will not construct A inverse directly.
Okay, sir.
Okay, so yeah, okay. This is fine. Or wait, let me be careful. This see, by mistake I removed the numpy, this array conversion, so this can give wrong results. So we have to check if it is. So it is safe to have A. Otherwise, it can give the transpose or something, right? So it can give np dot array of B and transpose it. Make it a column vector. Yeah. Yeah, it doesn't change, so no problem. It's the same. So this is fine. So this is how you do inverse. So these are basic matrix operations. So first thing, convert it to a numpy array. So you can do operations on this. Then you can do difference, scalar multiplication, element-wise multiplication, transpose, and stuff like this. You can get the inverse, etc. So anything else in matrices? I think these are mainly required, because ultimately what we'll do, as I said yesterday, we'll get a discretized form of the equations. We'll construct a system Ax equal to B, and we have to invert it to get the solution. After that, we'll do some post-processing. So matrix is central to our structural mechanics. Then functions, using functions in Python, right? So these are just functions very similar to C++ or C. So you define a function this way. Here you say define name of the function, and in brackets the argument of the function. So here is a function to compute the trace of a given square matrix. So you know that a trace of a matrix is what? It is the sum of the diagonal entries, right? So given a square matrix, this function will return the trace. So first I'm looking at the size of the matrix. So length of A is nothing but the size of the matrix. So number of rows in the matrix. So again, I'm using a for loop. So this is how, so remember how we use it. Whenever we want to add in a loop, just take the previous result and add the current entry to it. That's the trick. So start with, initialize the trace to be 0. Then you start with the 0 entry. Then you add 0, you add the first element 1 to 0. Then you go to the next entry, you go to the next loop, next iteration of the loop. So trace will have the value from the previous iteration, end of previous iteration, which is 1 in this case. And then add to it the second entry. So this is how you do it. So this is just finding the trace. The good thing about functions is, as you know, the reason for doing functions is you can reuse the same function. So I can also define a matrix C, which is say 4 cross 4. So C can be a 4 cross 4 matrix, say 1, 2, 3, -1, 4, 5, 4, -2. 6, 21, -40, 4, and 1, 1, 3, some 0. So I can reuse the same function. I can define the function as above. So function, this argument, as you know, is some kind of placeholder. Otherwise, what should I do? I should write the same loop for B and I should rewrite the same loop for C, right? If I have to reuse the same function again and again, I can just define a function. You don't have to run this block of code. You don't have to write this block of code once for B. And so imagine if we don't have function, I have to write this block size B is equal to length of B, trace is equal to this. For I in range size B, trace equal to trace plus B of I plus I. Then after defining C, I have to rewrite again. Size C is equal to something. Then for a loop over all the elements in C, I have to do all this. Instead, you can just say find trace of B. Find trace of C. So it's a coding convenience. You can reuse the same block of code without having to rewrite it again and again. Okay, I didn't run this. That's a problem. Let me run this. And I can run this. Okay, this is not printed. So I have to say print both. This one is 1 plus 5 is 6. 6 minus 40 is minus 34. And this should give 15. Yeah. So this completes some basic functions using Python. So any doubts? If you have, I'll wait for a while. You can also practice. I hope you had the chance to go through it in parallel. If you have any doubts, you can ask.
So for 3 cross 3 matrix, A matrix, how to find a separate element, A11, A12?
Okay,
For that,
okay. Yeah, for that, as I said, if you say for this, let us say this. Say this C matrix is there, which is 4 cross 4. If I want to get the second element in third row, which is 21, right? So I can say print A of, so start with the start count. So elements are, so rows are this way. So first index is row index. So 0, 1, 2. It is in row with index 2, but it's actually our third row. And column with index 1. So it is the second column, third row. So it is actually A32, but the indexing in Python starts with 0. So it is actually A21. So it is A of A square bracket 2 comma 1. And run it. Sorry, it's not A, it is C. It is C. For this matrix, it is C of 2 comma 1. What happened? Oh, okay. That's a problem. Okay, wait, I'll tell you. So this, if it is a list, you have to say square bracket 2, square bracket 1. Right? So, okay, I'll also put it this way. So if it is a list, if it is a 2D list, the syntax is you put A of A mn. This is nothing but AMN. The mnth entry of actually m minus 1, n minus 1. Okay, but if it is a numpy array, then you can put it as A m minus 1 comma n minus 1. So this will give AMN if it is a numpy array. So for example, if I make the same matrix as C, if I say C is np dot array of C. Now I made C as a matrix. So it is not a list anymore. It is a matrix itself. So once it is a matrix, you can say it is 2, 1. So earlier we saw when it was a list, it gave some weird error. Now I make it a NumPy array, then I can put it as 2, 1. So it will return 21. So this is another convenience with array. But now what is even more good is if we want to extract an entire, say, ith column of A, then that column is, if it is a NumPy array, so of A, which is a NumPy array, then you can access it by saying A of everything in the first in that column, comma I minus 1. So if you want ith column, you use this. You put a colon, which means so the row index is the first one, right? But you want all rows I minus ith column. So if I want the second column of C, I can say print C of colon comma 1. So this is the second column, 2, 5, 21, and 1. Now if I want ith row, say if we want to extract jth row of A, which is an NumPy array, then use A of a row number will come first. So it is j minus 1, comma, colon. So all the columns in that row. So say if I want the last row of C, so it is 3. 3 is the index of the last row. And here I put a colon. So I get this 1130. Yeah, that's a good question. This difference is important. So if it's an array, you can use, if it's a 2-dimensional list, you can use this square bracket indexing, just like how it is in C++, C. And if it is an NumPy array, you can use the comma index.
Understood, sir.
Okay. Any other doubts? So is everyone able to test it? Are you able to run such small codes now? Are you able to do it in the same file?
Yes, sir.
Okay.
Yes, sir.
Okay. So yeah, if you're able to follow, then fine. So now we can go to the actual programming part. Okay. So this is all. Anyway, this file will be saved. So I think in this, if I reopen it, it's probably saved. Yeah, so these changes I just made in the file are all saved. So you can refer to it in the Google Classroom. So the next part of it is assembly. So we have done this. Next, we'll start with the assembly. So, okay, I'll open yesterday's presentation. Yeah, so we saw that to recap what we did yesterday, we started with nodes and elements. Nodes are where we are interested in degrees of freedom, and elements are something that connects two nodes. And first, what we did was we developed the force displacement relationship for an element with two nodes. So forces and displacements are applied at the ends of the nodes, and conditions of equilibrium, stress strain relations, and not compatibility. Equilibrium and stress strain relations give us some kind of a matrix relationship between the force vector and the displacement vector. So the force vector is the collection of end forces F1 and F2, which is denoted in green, and the displacement vector is the collection of displacements U1 and U2, which is denoted in pink. So we get a matrix relationship like this, where K11 is minus AE by L, K12 and K21 are minus AE by L, and K22 is AE by L for a bar element, where A is the area, E is the Young's modulus, and L is the length of the element. Now, then what we saw was, this is for one element, but the system has got more than one element, and they're connected at a certain node. So there is a shared node here. Right? We saw that there is a shared node here. So what to do? At the shared node, the displacements are not independent. For compatibility to hold, the displacements have to be equal. Otherwise, this element will get disconnected from the next element. That cannot happen. So the whatever deformation the two elements undergo, the deformations have to be compatible. And by compatible, we mean that the displacement field is continuous. So after the deformation, you cannot have two elements going away separately or the two elements penetrating into each other. So compatibility requires these two are equal, and the force equilibrium requires that the net force on the joint, which is F2 plus F2 of 1 plus F1 of 2 is equal to the total external force applied, which is F2. So these two are the conditions. And so F2 of 1 is given by this last row of this equation, and F1 of 2 is given by the first row of this equation. So you add the two. We add the last row and the first row here with appropriate, right? So we have to make sure that the right hand side is the displacements are correct. So write out the equations, add them. So U2 has a common, U2 is common in both the equations. U1 and U3 are not common. So U2 is common in both the equations. So the coefficient of U2 will become K22 of 1 plus K11 of 2. So we get something like this. Then you append zeros to the first equation and the last equation. So you get a 3 cross 3 system. So you have a system that is relating three forces to three displacements. So for one element, we had two forces and two displacements, and we got a relationship between the two. For an assembly of two elements, which has got three nodes, we have three forces and three displacements, and the relationship is something like this. So what we see is we take the element stiffness matrix and arrange it in a certain format. Wherever there is an overlap, wherever there's a common shared node, the matrices overlap. And whenever there's an overlap, add the stiffness coefficient. That was the rule that we had to follow. And this can be extended to a system of n number of elements as follows. So wherever there's an overlap, the coefficients, matrix coefficients get added up. Then what we saw, so this is basically the logic. This is basically the logic. Now, so first, so we are going to program this in Python very soon. But before programming, we need what is called an algorithm, which is the stepwise procedure of how we are going to do it. So think about it, and yeah, think about it this way. So first, I have a global stiffness matrix. What I want to get is a 1 minute. So if what I want to get is a global stiffness matrix, which relates. Okay, so what was the size of the global stiffness matrix? So suppose I have m number of degrees of freedom, or suppose I have m elements and n degrees of freedom, or nodes. It's a problem with. I'll use the one node. Okay, so yeah. So suppose I have a system, a connected system of elements like this. Doesn't matter, whatever it is. And at every node, I'm having some degree of freedom. So in 1D, there's only 1D bar, there's only 1 degree of freedom per node. Suppose I have m elements and n degrees of freedom. So what is the size of stiffness matrix? So any guess?
N cross N, sir.
Yeah, n cross n is correct. So what is the reasoning for that?
N is the number of nodes.
Okay, so n is the number of nodes. So size involves 2 n's, right? So why should that be? It cannot be 1 cross n, 2 cross n. Why is it n cross n? Think about what the global stiffness matrix relates. So you will get the answer. The global stiffness matrix relates something to something.
It is formed from stiffness matrix of individual elements.
Okay. But m doesn't even appear here. Right? Note m, the number of elements doesn't even appear here. Yeah, it is correct. The global stiffness matrix is evaluated from the local element stiffness matrices. But fundamentally, why do we need the global stiffness matrix? So it relates the displacements at the nodes to the forces at the nodes, right? So these are U1, U2, UN. So so these are the nodal displacements. We have n nodes, right? So this is the number of nodes, and at every node we have displacement, and for n nodes we have n number of nodal displacements, and these are the nodal forces. So if you recall the presentation, you see what it is relating, F1, F2 up to Fn, which are the forces applied at node 1, force at node 2, F3 is force at node 3, and Fn is the force at node n. Similarly, U1 is the displacement of node 1, U2 is the displacement of node 2, and Un is the displacement of node n. So it is relating the force at every node to the displacements at every node. So it's like, so this number of, how many nodal forces we'll have? We'll have n cross 1. And what is the size of nodal displacement matrix? It is n cross 1. So this matrix has to relate, it has to take in a vector and return another vector. So it's an operator. So this, the number of rows in this matrix should be equal to the left-hand side, and the number of columns in the matrix should be equal to what it acts on. So the size of a global stiffness matrix is n cross n. Okay. So is this clear? It's very fundamental. The size of the global, yeah. So the reason why it has got n cross n is it relates n forces to n displacements. So it can be only n cross n. It cannot be anything else. Okay. Okay, so how do we do it? So we are going to do the assembly operation now. So now look at these two images carefully. Look at these two images carefully. You have something, yeah, I am denoting this node as U1 of 1. So this is the first node of element 1. And this node is the same as this node, right? The first node of element 1 is the globally node 1. So this globally I'm calling it as U1, U2, U3, etc. And locally for this element, this is the first node. And here, what is the case? Here, the second node of first element is globally U2. So that was the compatibility relation. If you recall, the compatibility relation was U2 of 1 is equal to U1, which is also, sorry, U2, which is also U1 of 2. And what are the other compatibility relations? U1 of 1 is U1 and U2 of 2 is U3. So U2 of 1 is U2 and U1 of 2 is also U2. So these two nodes are connected. So they both together, you can call it by this degree of freedom. And similarly, U2 of 2 is actually, it goes here, U3. So while assembling, we have to have these in mind. So which two will overlap? Which two entries will overlap?
U2 of 1 and U1 of 2.
Those are the degrees of freedom. But what will actually overlap? Is it the that's so you have stiffness matrix. Something overlaps here. Here it is 0. And here you have either U2 of 1 and U1. So which is U2, U1, U2, U3. So which entries will overlap here? Whatever is multiplying
2
U2.
and 1 1.
Yeah. So K22 of 1 and K11 of 2 will overlap here. Right. So that is the rule. So whenever but doing it the other way is difficult. Suppose you start with an element, you can see where this element will fit in. But if you start with a global node, you cannot see what are all the elements that contribute to that. So if you take U2, it is difficult to see that U2 of 1, and it is not difficult. Here it is easy because there are only two nodes, two elements contributing to this. But suppose you have a truss. You have a truss. So we'll be doing truss maybe next session. So as truss discretization also very similar. You have what is called nodes and elements. If you take this node, and say this is element 1, 2, 3, 4, 5, 6, 7, 8, and 9. So what are all the what are the elements that are connected to it? So the second node of 1, first node of 2, assuming these all are oriented, the elements are all like this. First node of 4 and first node of 5. So if we look at it with our eyes, if we look at a diagram with our eyes, we can say which are all the elements connected to a given node. But when you are doing it on a computer, there is no diagram for the computer to look at. So the computer doesn't look at the diagram and it doesn't give the node numbers that way. So the assembly operation has to be carried out in a systematic manner. So you have to do some systematic assembly. So how do we do it? So one approach. So approach 1 is what? You look at a node, identify the elements connected to it. Right, then see if this node is the first or second element. So see if this node, say, let me call the node A. Look at a node A, see if this node A is the first or second element of the second node of element, every element connected to it. Only then you can overlap correctly, right? So every element connected to it. Then add up accordingly. Then you add up accordingly. So this requires you take every node, see if it is lying in element 1, element 2, element 3, element 4. You check what are all the elements having it. Then go to that element, see if the first node is that node or the second node is that node, and then put it in this. So this is a tedious approach, tedious on a computer. But for a human, it is easy. tedious on a computer. Because we can visually see with our eyes that these are the elements connected, but the input given to a computer is not a diagram. It is all in terms of numbers. So how do we do it, right? So then we go to approach 2. One thing, let me make it black. So what is the second approach? So it is like, suppose you have different pieces of a jigsaw puzzle, right? You want to put together and form some pattern. One approach is you see what has to come here, check every puzzle, every piece, and then select the ones and put it in that place. The other approach is when you take a piece, you see where that piece has to fit in and fit it in the appropriate place. So you have many pieces that have to fit together to form some image or some structure. One approach is you see what are all the, you go to every point and see which piece will fit in there. That is one approach. That is basically this approach, right? Look at a node and see what elements are coming there. The other approach is pick a piece and see where it will fit in. Both of this will end up in the same final result, but one of them will be faster. In the first case, you have to search through every piece and see it will fit in or not. In the second case, you just see, you take an element and see where it will fit in. So in approach 2, what you do is pick an element. Then look at its first node. So pick an element E, look at its first node. So element in our case has got 2 nodes. Look at its first node. Let us call that node as E1. Now you see where E1 will fit in. So where should E1 go? You see where E1 goes. Say that goes, so it goes to some point, right? So okay, so at this point I should go to some diagram, right? So this is element 1. First approach is I go to this global node 1. I see what are all the elements connected to global node 1. What are all the elements connected to global node 1? This is global node 1, global node 2, global node 3.
First element only, sir.
First element. And in the first element, global node 1 is first node or second node?
First node.
First node. So that is one way. That is the first way. The second way is you pick the first element. You pick the first element, call it E1. Sorry, call it something. Call it E. Then you look at the first node of this element. So this you call it E1. And this node you call it E2. Now you can ask the question, where should E1 go in the global? So corresponding to E1, what is the global node number? Where is E1 going to? 1. And where is E2 going to?
2.
2. So this element you call it as F. Where is F1 going to? Where is F1 going to?
F1. The force in element 2, no, sir.
No, F is not force. I'm calling okay, make it G. Element 2 is G. So where is G1 is the node in node 1 of element 2. So where is G1 going to?
2.
2. And where is G2 going to?
3.
Yeah, this is going to 3. So you see there is a mapping here. We have a mapping. So for element jth node of element I goes to global node K. Something like this. Right? You have a relationship like this. You pick an element, then you see where the first node of that element goes, and then where the second node of that element goes. So that has a mapping like this. You say in our case, we saw E1 goes to 1, E2 goes to 2, G1 goes to 2 and G2 goes to 3. So what is this? This is a mapping, right? This is a function. So on the one side, you have the local node numbers. And on the other side, you're having the global node numbers. So this is a set. This is a set. Call this set A. Call this set B. You have something that relates the elements of set A to set B. And this takes all elements in set A and relates exactly to one element in set B. So it is a function. So this is a function or a mapping. So one local node cannot be in two global nodes. That is not allowed, right? One local node cannot be in two global nodes. That is junk. But two local nodes can be in one global node when they are connected. So it is a mapping or a function. So this function is called the local to global mapping, or you just call it as assembly node. So here, this is the thing. So first node of element 1 is global node 1. So call the global node. So this is what is it. So jth node of element I is global node M. So this is a mapping that we are looking at. So what this mapping has to return, if I give I comma j, if I give the element number and the node number in that element, this mapping has to return the global node number. So this is a systematic way of assembling the global stiffness matrix. Okay, so yeah, any doubts here? I have to stop here. Any doubts? Is it clear?
Yes, sir.
Okay. Others also? Is there any doubt if anybody else has? Yeah, you can acknowledge if there are no doubts. I can.
No doubt, sir.
Okay. Okay. So have this mapping in mind. Okay. So this is important. Okay. So I have this in mind. So this this local to global mapping is important. Now let's get to the algorithm for assembly. So start with initializing the global stiffness matrix and the global force matrix. Okay, so as I said, what is the global stiffness matrix size? It relates n nodal forces to n displacement. So it is n cross n. So just set it as some zeros. Fill it up with zeros. Right, you just fill it up with zeros. N cross n zero matrix. Why we are doing that, we'll see, right? We'll see why we are doing that. So what is the idea? We take every element. So loop over all elements. So for ith element, you take the ith element. Then for the ith element, you can compute the element stiffness matrix, right? So give for the ith element will have an A, it will have an E, it will have an L. The length ith element will have a length, it will have a Young's modulus, it will have an area. Then you compute the element stiffness matrix K of I. So this is the element stiffness matrix of the ith element. Then look at the jth node of element 1. So what are the values j can take?
One or two.
Yeah, it can be 1 or 2. Then look at this mapping, right? So we need this mapping which relates every local node number and the element number to the global node number. Then you do this kind of an update. So you see what this does. You see what this one basically does. You say k of yeah. So this is okay. So you take k of m comma m. So m comma m is actually it relates a global node m. Yeah. So this there is some. So you take the global stiffness matrix k of m comma m. and you're looking at the diagonal entries of the global stiffness matrix. So for every node, you know the contribution from that node to the element, right? So if you have suppose you have this in this case. So in the ith stiffness matrix, take the diagonal entries j comma j. So if you take the first node, you get it gets added to some. So for example, take this element, second element. So here I is equal to 2, and in this element take j is equal to 1, which is actually this node. And say the global node numbers are 1, 2, 3, 4. So what is m of 2 comma 1? So what is the first node of second element? Sorry, m, or what is it? A. Yeah, m is equal to some assembly of 2 comma 1. What it is? It is. So in second element, first node is, what is the global node number?
2, sir.
2. So this will contribute this from this element. There will be a contribution to this node. So you take the stiffness matrix, global stiffness matrix of this, and update it. It gets a contribution from this element. So add the contribution. Then similarly, similarly, what is m of 2 comma 2? It is
3, sir.
3. Right? So this node will also get a contribution from this element. Now if you go to the next element, now go to I is equal to 3. So I is equal to 3, j is equal to 1. What is m? It is 3. But 3 will also get a contribution from the element 3. So k of 3 comma 3 will be what? It will already have the contribution from element 2. So let us say it is already k22 of 2 by this iteration. When you add element 3, it will also get k11. So j is 1, I is 3. So this will get added up. The contributions from element 2 and 3 will get added up if you do this scheme. And this is only for the diagonal entry. So we'll see what is to be done for non-diagonal entries, off-diagonal entries, right? So you see, at least for the bar problem, the overlap is only in the diagonal entries, not in the off-diagonal entries. So this scheme will basically work. First, initialize, make everything 0. So if a node is not visited, it will remain 0. But if you have visited an element that contains the node, that will get updated with the contribution from that element. Now you go to the next element. If it is containing a shared node, and that shared node is already getting a contribution from some other element, when you do this update for the current element, it will contribute to the shared node. So this will become clear when we actually program it. Now let's go to the programming part. So this algorithm may not be clear right now, but if it's clear, I'm happy. But when we program it, anyway, it will become clear. So yeah, this programming is what we are going to do right now. You can open the Google Classroom thing. Open this. So maybe you can make a copy and then you can open it. So just go to this. Just click Google, open with Google Colab. And then file, make save a copy in Drive. Yeah, so once you get copy of something, you start editing in that. So this, maybe I'll name it with my name, and I'll edit in this so that the original doesn't change. Okay, so yeah, but I will make the changes in the original one, so you have the edits, but you people, you can work on the copy. So now we are first, yeah. So so now we are going to solve this problem with bar elements. Okay, so right now we don't know what the bar element is. but there are different steps. So one step is, first step is, okay. So here we need to define a problem. So here, let me say problem definition. So we have to define a problem. Right. So here problem definition, I'll tell what it is. Then we have to assemble the global stiffness matrix. So we'll write a function, right? Because all of the finite element codes that we use, all the finite element, we don't want to assemble the global stiffness for every problem. So we'll write a function to assemble the global stiffness. Now you can just as yesterday, you can tell me the steps of how we assemble. So for your convenience, I'll put this slideshow on one side, and here is the algorithm. Here's the code. So in Teams, there's also option called focus mode. So I can go to this view, focus on content, right? For me, it is disabled because I am presenting it. But you people can select focus on content so that the participants are hidden and you'll see a bigger screen. So you can. Now I'm going to code this global stiffness assembly. So yeah, so just as yesterday, you can take turns and tell me what are the steps. So what should be the first line of the code?
Define a matrix K. Then K is
yes,
equal
that's
to
zeros, right? K is filled with zeros. Perfect. So that is correct. I'll zoom in so that it's visible for all of you. Yeah, so we have to write a. Yeah, so this is the algorithm. So first step is, so note that you need to have this indentation. You need to have a small gap here because it is inside the function, right? So make sure you don't make that mistake. So I define a function. I'll start with a zero matrix, right? So I'll start with zero so that I can add numbers to zero. So K, I'm writing it as. So if to initialize with zeros, you have to use numpy dot zeros. What is the size of the matrix? So here I'll have size. Okay, so this one will not run because I have not defined size. But what is the size of this matrix?
3, sir.
No, not 3. This is a general code. So we don't know the number of. So this is for any number of nodes, right? So you see what are the inputs to this function? We have A, we have E, we have nodes and the elements, right? So nodes is the list of nodes and elements is the list of elements. So let me call size of, let me say num nodes. I'll call a variable number of nodes is equal to length of this array nodes. Okay, so what is the size of K?
Nodes. Num underscore nodes.
Okay, comma num underscore nodes, right? It is a square matrix, so it is 3 n cross n, and this will fill it up with zeros everywhere, right? So if you want to check it is doing the right thing. Okay, so what I'll do is, if I have to show it somewhere else, so this is our main code. Just I'm adding something here just to say n is equal to 3, and if I say k is equal to np dot zeros n comma n. Before that, I should import numpy. Have I done it? Yeah, I have imported numpy. So run this piece first. The import has to run first. It says it's connecting to Python. Okay, so this piece I can run. Now if I print K, what is K? If I print it, it is 0, 0, 0, 0, 0, 0, 0. So if I put n is equal to 10, it will print a 10 cross 10 array. So okay, so this piece is fine. So the first line is fine. We are initializing K as a 0 matrix of size n cross n. Okay, then what is the next? Let me. Yeah, so what is the next step? We initialized it, then you can see it may be too small, but so what is the next step? What should I do here? The next step is loop over all the elements. So how do I do it? How do I write a loop?
For I in range of n.
So one thing, I'll use a double I because in MATLAB, sorry, in Python, the complex variable I is also denoted by I. So this is just to be safe. So we don't want to confuse with square root of -1, right? So whenever I want to put I, I'll put double I. Whenever I want to J, I'll put double J. That's just a convenience to avoid confusions. So yeah, it's correct. The step is correct for I in range of length
num
of
of
elements, right? They have some number of elements. So, okay, if you want that, I'll say num elements. We want to loop over all elements. So I'll say number of elements is equal to the length of the array elements. Okay, so I'll say it is num range of you're looping over all the elements, not the nodes, right? So it is num elements. Okay, I'm looping over all elements. Then what should I do? Okay, I feel you're struggling, so I'll do one thing. I'll solve the problem manually, and then we'll replicate the same steps in Python. So here the title is solving bar problem manually, but using the algorithm. Okay, so suppose we have no. Let us start with the physical problem. We have two ends fixed. We have a bar in between, and at the center of the bar, I'm applying a force F. Right now, I'm trying to solve this problem using this matrix analysis. So I'm discretizing this with two elements. So wherever I'm applying a node, I'm putting one node. So this is node 1, node 2, node 3. And this is element 1, this is element 2. Okay. And now at this point, I'm applying a force F. And this end is fixed, this end is fixed. So this is the problem that I want to solve. Now, first, if you want to solve it without, so let us say it has the cross-sectional properties are some AE by L, sorry, AEL. This has AEL. So total length is 2L. Now this is the problem that I want to solve. So the strength of materials, whatever using the conventional means, how do you solve it? How do you solve it? You draw a free body diagram of the region before this. So this has got some force tension T1. This is subjected to some tension T2. So if you want to get, so this is like strength of material solution. So at the joint, you have forces T1 minus T2, right? So this is the joint. On the joint, we are applying a force F here. So this is subjected to T2, T1. So T1 is equal to T2 plus F. This is one condition. This is a condition for equilibrium. And these are all two force members. So what is the strain in the member? Or what is the stress in the first member? Sigma 1 is equal to T1 by A. Strain in the first member is T1 by AE. So what is the displacement? Delta L of the first member. What is it? It's just epsilon 1 into L, right? So it is T1 L by AE. So the first member has extended by delta L1. Right? The first member has extended by delta L1. And what about the second member? The second member, it is say stress is T2 by A. The strain is T2 by AE. And delta L2 is what? Epsilon 2L, which is T2L by AE. So the first member has extended by delta L1. The second member has extended by some delta L2. What is the compatibility condition?
Del L1 is equal to del L2.
Del L1 is equal to?
Del L2, sir.
No, that is not the compatibility. Both are in tension, remember. So if both are equally extending, then both have interpenetrated, right? So here the, sorry? Sorry, I couldn't hear. It was breaking. Could you repeat?
Minus del of L2.
Correct. It is minus del of L2, minus del L2. Or in alternatively, you can say, yeah. So this is another trick in strength of materials problems. So when you see delta L1 plus delta L2 is the total extension of this rod, right? So this piece extends by delta L1, this piece extends by delta L2, which means the total extension of the rod is delta L1 plus delta L2. But the rod cannot extend itself because it is fixed at both ends. So delta L is equal to delta L1 plus delta L2 is equal to 0. This is the compatibility condition. Now you do this. So what do we get? We get so we have to say delta L1 plus delta L2 is equal to 0. This is one condition. So what is it? T1 L by AE plus T2 L by AE is equal to 0. So this you can also write it as T1 plus T2 is equal to 0. And what is the other equation? This is compatibility equation, and equilibrium equation is T1 is equal to T2 plus F. So the other equation is T1 is equal to T2 plus F. Solve this, you get T2 T2 is equal to minus F. So T2 is equal to minus F by 2. So what is delta L2? It is minus FL by 2AE, which means delta L1 is FL by 2AE. But what is delta L1? It is the displacement of the middle point, right? The middle point to the right. So we have, by the strength of materials approach, the middle point has moved by midpoint has moved to the right by FL by 2AE. So this is the strength of material solution. So okay, there's no coding or this doesn't need any. So this is a simple problem by strength of materials. Now using the matrix approach, you have to get the same solution, right? So now tell me the steps in matrix approach. So first step is we initialize a stiffness matrix of size 3 cross 3. So I'll say K is equal to 0, 0, 0, 0, 0, 0, 0, 0, 0. So this, what is the size of the stiffness matrix? It is num nodes by number of nodes. Now, how will I give this problem to the computer? So I should give the location of these nodes, right? So I'll give an array nodes. Remember, here you're not supposed to look at the diagram. Here it is okay. Here you can draw a free body diagram, visually look at the signs of the forces, add them up, establish equilibrium. All this can be done when you're looking at the figures. But when you give it to a computer, it cannot see figures. So everything that you have to give has to be in the form of numbers. So you give an array called nodes, which gives the location of these nodes. So what is the location of these nodes? The first node is at location. So first entry of the nodes array will be the x coordinate of the first node. So what is the first entry? What is the first entry of nodes array? I said it's the x coordinate of the node 1. So what is it? Okay, well, if I put a coordinate system here, starting with x, so it is 0. What is the x coordinate of node 2?
L.
And x coordinate of node 3 is
2L.
2L. Yes. So this is the nodes array. Now I'll give an elements array to the computer. So how will I give the elements array to the computer? So what I want to say, what is the information that I want to tell about this element? This element has got area A, Young's modulus E, and length. Length L is not important. So why is it not important? If I know the two nodes that are connected to the element, then I know where this element will fit in and also its length. So L is not an independent information. A and E are independent. So the cross-sectional properties and the Young's modulus of this element are important. And apart from that, what is required? What are the nodes connected to this element? So in our problems, later we'll go on to non-uniform members, but at least for the first set, let us take all the elements have the area A and Young's modulus E. So what are the nodes connected to element 1? And what are the nodes connected to element 1?
1 and 2.
L.
Sorry? 0L you said, is it? No, not required. 0L is the x coordinate of the nodes. We want the node numbers connected to 1 and element 1, right? These two are different. So 0 and L are the x coordinates of element ends of the element. But what I am asking is node as a node itself. So you have to be careful. So right, I hope you understand that. We want to see the nodes connected to element 1. So not the x coordinate of the nodes connected to element 1. Okay, so this is element 1. And what is it for element 2?
2 and 3.
2 and
2 and 3, perfect. Okay, now this is correct. So we are giving this information to the computer. So you see, suppose given this information, can you make the drawing, right? Given this information, you can easily make the drawing. So you make an element 1. Element 1 is connected to nodes 1 and 2. You draw an element 2. Element 2 is connected to nodes 2 and 3. And you know the lengths of, you know the locations of node 1, 2, and 3. So this completely specifies the drawing. So given this, you're able to recreate the drawing. Therefore, this information is complete. Okay, this information is complete. So now you're giving the complete information to the computer. So let's do that. So I'll do that. This is not required. I'll delete this piece. Yeah. So this is so I'm doing problem definition right now. Okay, so let me. So when I said I hope my screen is visible. So in problem definition, I'm defining A and E as just 1 and 1 for all the elements, and nodes I'm giving at 0, 0.5, and 1. So let's just make it consistent with whatever I defined there, 0, 1, and 2. So this so which means I'm taking L also as 1, right? So I'm taking L as 1, AE as 1, E as 1. Therefore, the nodes are located at 0, L, and 2L. So this is the location of the nodes. So this is the nodes array, and elements array is what? We saw it is 1, 2 and 2, 3. But you know in Python numbering starts at 0. It is 0, 1 and 1, 2. And what are the boundary nodes? Boundary nodes are the first node and the third node. So I'm saying that the fixed nodes are at 0 and 2. The node 1 and node 3 are fixed. So it corresponds to index 0 and index 2. Okay, so this is problem is defined now. Next, what should I do? What is the second step? We have to assemble, right? So we have already defined. So next second step is assemble. For assembly, what are my steps? First, I have to loop over all elements. Python notation. So I equal to 0 is the first element. Now I look at the first element. I'm in the first element. Now I'm looking at what are the nodes connected to that element, right? What is the first node of element 1? What is the first node of
1?
Yeah, I is equal to 0, j is equal to 0. It is equal to 1. But again in Python notation, you can say it is 0. Or rather, let me use one notation consistently. So let us make this first element. For I equal to 1, j equal to 1, this is 1. And what is the second node of first element? It is
2.
2. Correct. Where did you get this information from? You can get this information from this matrix, elements matrix, right? Because I cannot see this anymore. Don't look at the figure. Just look at this matrix. You have 1, 2 information here. Now from this, what should I do? What is my next step? This is okay. I have identified. Now can we find out the length of element 1? What is length of the element? So the length of the element is L. It is x2 minus x1 for the element. But what is x2? X2 is nodes of 2 minus nodes of 1, right? In the nodes array, I'm having x1, x2, and x3. So the length of the first element is x2 minus x1. Now I'm looking at the nodes in the nodes array. What is the second entry minus the nodes array? What is the first entry? So this is L minus 0, which is L. So this is the length of element 1. It is L. And AE is just AE. Next, what is the step? I have to construct the element stiffness matrix. Element stiffness matrix for the first element. Right? So what it is? So the element stiffness matrix for the first element is what? How many elements, how many entries it has? What is the size of this matrix?
2 cross 2 matrix.
Yeah, it relates two displacements to two forces. Okay. What are the entries?
AE by L minus.
Yeah, minus AE by L.
Minus
AE by
and
and
AE.
AE by. Yes. So this is correct. Very good. Now, what is the next step? I have to take the element stiffness entries and plug it into the global stiffness matrix. So I take so now what happens? Global stiffness matrix of 1, 1 will be global stiffness matrix of 1, 1 plus the element stiffness matrix of. So I'm using capital K for the global stiffness matrix and small k for the element stiffness. In the element stiffness matrix, which element will go there? This one, right? 1, 1. So global stiffness matrix, and I'll put all the four together. So K 1, 2 is K of 1, 2 plus the local matrix, it is 1, 2. So we saw here, right? Local node 1 goes to global node 1, local node 2 goes to global node 2. So similarly, k of 2, 1 is k of 2, 1 plus local of 2, 1, and k of 2, 2 is k of 2, 2 plus element stiffness of 2, 2. Now all these are 0. In this initially, this is the first iteration, so the entire matrix is empty. So what will K become by the end of this first iteration? K is 3 cross 3, right? Sorry.
Small k 1, 1.
So what is small k 1, 1? We just wrote it above.
AE by L, sir.
Yeah. So this will be AE by L. Second entry?
Minus AE by L.
Okay.
0.
Okay.
0.
Is it 0?
Minus
This is 2,
AE by
1. This is 2, 1, right? K of 2, 1 is k of 2, 1 plus local of 2, 1. So this is updated. So this is not 0. Minus AE by L. Here?
0.
AE by
No, this is not 0. We have k1 of 2. So k of 2, 2 is k1 of 2, 2. And k1 of 2, 2 is AE by L. And here?
0. 0.
And
zeros.
yeah, in the third row, it is not updated. So it is 0. Right? So you have to be careful. So these 4 are non-zero values, but this is all 0. Initially, by the end of before the first iteration, the matrix is empty, and you're plugging in these values. Now so this is done. We have assembled one element into the system. Now go to element 2. So I equal to 2, element 2. Now what is local node 1 is what? Local node 1 is global node. So don't look at the, yeah, it is just M of I equal to 2, J equal to 1. And this is 2. Look at this one. So in the second element, first node is 2. And similarly, in the second element, second node is M of I equal to 2, J equal to 2. What it is from this matrix? Yeah. See only the matrix, not the image. So it is 3. Now, so this is done. So similarly, what is L for this? L for element 2 is x3 minus x2. Right? Second node minus first node. What is x3 minus x2? It is 2L minus L.
Yes.
It is L.
Yes.
Yes, perfect. It is L. Now, what is the element stiffness matrix for this? AE is same. So it is the same as the first one. AE by L
Minus AE
minus
by
AE by L minus AE by L.
Minus AE by L.
L. Yes. Now let's do the plugging in operation. Now what is K at the beginning? So here what is the idea? So here where we should plug in all the 1 entries will go into 2 and 2 entries will go into 3. So K of 2, 2 is what? It is K of 2, 2 plus K in this element. Which one will go there?
1, 1.
1, 1. Perfect. So here the idea is you're having an ij locally. So this entry you're picking up, where it will go, local number is 1, 1. But local 1, 1 means it is actually m, m is 2, 2. Similarly, K of 2, 3 is what? It will be 2, 3. Why? Because this is 1, 2, which is 2, 3. So this will go to like this, right? So or start from the right hand side. So where will 2, 1 go? And where will 2, 2 go? K2 of 2, 2. So these have to go somewhere. We'll see where it goes. So K of 1, 2 goes to 2, 3. And 2, 1 will go to 3, 2, right? So K of 3, 2 will get K of Yeah, 3 comma 2 plus this, and here k of 3 comma 3 will be yes. Very good. Now what before doing this addition, what was k before, right? Before I equal to 2, remember what is k? I don't have to write it again. I'll take this. This is k. This is k before, and at I is equal to 2. At I is equal to 2, I'm doing all these updates. So 2 comma 2 will get one more contribution from this. So AE by L get added to 2 comma 2. So here I'm adding another AE by L. And here what will happen? To this I'm adding 1 comma 2, what I'm adding? Minus AE by L, right? So to this I'm adding minus AE by L. And 3 comma 2 gets updated with 2 comma 1. And 2 comma 1 is minus AE by L. And 3 comma 3 gets updated with 2 comma 2. What is 2 comma 2?
AE by L.
AE by L. So by the end of I is equal to 2, I have k as what? It is. I'll take the E by L commonly out. It's a mess writing it everywhere. So k, this is capital K, is AE by L. What do I get? 1 minus 1 0 minus 1
2
or 2 minus 1 0 minus 1 1. Now this is the global stiffness matrix. So this is the assembly operation, right? So now you understand the process. So what is the total system we have? K is this AE by L, 1 minus 1 0 minus 1 2 minus 1 0 minus 1 1. This multiplying U1 U2 U3 is equal to F1 F2 F3. So what are the forces that I'm applying? At the leftmost end, I'm having some reaction F1. And middle, I have an applied force F. And the right side, I have some reaction F3. We don't know what they are, but we know this. So this is the system we are having. What is the next step? We have to impose the boundary condition, right? So next step is boundary condition. Now, do we know F1? Do we know F1? No. Until we solve the problem, we don't know the reaction. It is a statically indeterminate structure. You cannot get F1 directly from some equilibrium conditions, right? You cannot get F1 directly. So we don't know F1. But do we know U1?
Yes, sir.
Yes. What it is?
It is
So this
fixed
answer
in
is
0.
0. And similarly, U3 is 0. So in the first set, in this set of equations, look at the first equation, right? The first equation says U1 minus U2 is equal to F1. But we don't really know what F1 is. So instead of the first equation, I can replace the first equation with U1 is equal to 0. So what I'm doing is I'll replace the first equation as I take the A by L inside because now it's no longer common. So in place of the first equation, I can put U1 is equal to 0. So what are the coefficients of U1 equal to 0? It's like 1, 0, 0, U1, U2, U3 is equal to 0, 0, 0. Sorry, is equal to 0. It's a scalar, right? So this is 1 cross 3, this is 3 cross 1. So it's like 1 U1 plus 0 U2 plus 0 U3 is equal to 0. So I can replace the first equation as 1, 0, 0. Second equation, you have it as it is, minus AE by L, 2 AE by L, minus AE by L. And bottom you have, similarly, U3 is equal to 0. You can write it as 0, 0, 1, U1, U2, U3 is equal to 0. So the third equation is 0, 0, 1. U1, U2, U3 is equal to On the right hand side, what is there now? It is 0. It's not F1 now. So first equation is U1 equal to 0. Second equation is second equation is unchanged, right? Whenever you don't have a boundary node, it is unchanged. The third equation is 0. Now, can this equation, this can be solved? Yes. So now solve this system of equation. So fourth step is solve. So 3 cross 3, but you can eliminate a lot of things. U3 is equal to 0. U1 is equal to 0. So if you look at the third equation, it is just 2AE by L. So you get 0 plus 2AE by L U2 plus 0 is equal to F. So you get U2 is equal to FL by 2AE. So this is the same answer we got by the strength of materials approach. Right, so these are the steps. Now have this in mind and we are going to code it, right? So we'll go to this. Now tell me the steps. So I felt you were struggling at that time. So we have given we have made the problem definition in a way that the computer can understand. So first step is done. We have defined AE, we have an array of nodes and we have an array of elements. And we also have given the boundary conditions. The next step is we have to assemble. So step 2, it is we have to assemble the stiffness. Assemble the stiffness matrix. Okay. Now, how do we assemble the stiffness matrix? So that's what we are writing. So this step is fine. We said we'll initialize K with a 0 matrix. Then we are taking every element. Okay. So what did I do? Now what should I do? What is node 1 of element? What is node 1 for this ith element? Which array I should look at? I should look at the elements array, right?
Yes, sir.
So node 1 is elements of IA comma 1. So in ith element, what is the first node? So which will, in this case, what will give it? In the ith element, first node is 0. So yeah, I shouldn't put 1 here, I should put 0. Okay, I'll use the list notation because I have not made it an array yet. Similarly, what is node 2? Node 2 is LMs of IA. What should I put here?
1.
1, yeah. So recall the steps, right? So I'm going to first element. Yeah, I'm going to first element. I'm saying what is j equal to 1, j equal to 2. It is 1 and 2. But that I'm doing it in a general form. I don't need to do it for every element. I'm writing one code and looping over all this. Then what am I doing? I'm finding the length of the element, right? So then I'm finding length of this element. So length of this element is what? It is x2 minus x1. And what is x2? Which array will give us x2? See here.
Nodes.
Nodes array. So I have to take nodes of node 2, right? I have to take nodes of node 2 minus nodes of node 1. So this will give the length of this element. Then what I'm doing? Then I'm constructing the element stiffness matrix. So I have a function for that. I have a function for the def bar stiffness. So I'll say K is equal to bar stiffness of bar stiffness of what all should go into bar stiffness? For finding the element stiffness matrix, I just need A, E, and L, right? So this has to take only A, E, and L as inputs. So we have not written the function yet, but we will write it soon. Okay, so this is simple. So here this is easy. Like now you have to tell me the code. So how do I write down the bar element stiffness matrix? What is the first step? Like this has to return the element stiffness matrix given AE by L. So what it is? Okay, is it difficult? It is easy, right?
2 cross 2 matrix of 1 minus 1 minus 1 and 1.
Okay. So I say I'll call it K. K is what?
AE by L
AE by
multiplying 2 cross 2
1.
matrix. So 2 cross 2 matrix, I'll initialize with this array. So it is 1
minus 1,
and then
comma,
again.
comma
Yes.
1.
Yes. Okay, so we have computed it. Then what I should do? Return it, right? Return k. So wherever this is called, it will return this number, this matrix. So this is an NP matrix. So this is an NP array, right? Otherwise, you will have to use the list notation. So it's fine. So I got the k here. Next, what should I do? I have to do this update, right? I have to do this update. What is this update here? So this on the left hand side, you have the global nodes, which I am calling as node 1 and node 2. On the right hand side, I have the local nodes, which are just 1 and 2. So what is the update here? So this is update the global stiffness. So k of what? What should come? What should come here?
1, comma 1.
1, comma 1 or 1, comma 1 is the local node number or global node number?
Global node number.
Global node number. So, but remember, this is a general code. So this will be called over every element. So when I go to the next element, this has to be 2, comma 2. So what should I do here? I've already stored that variable in node 1, right? So node 1 is the global node corresponding to, yeah, it is node 1, comma node 1. This is equal to what? K of
node 1, comma node 1 plus
Node 1
plus
plus small k of node 1, comma
no, small k of node 1, comma node 1 means suppose it is element 2, node 2 will be 3, comma 3, but small k is always of the size 2 cross 2, right? So here this is global node number, and here what is it? It is a local node number, right? So in the second element, you have 2, comma 2, and here you have 1, comma 1. So it's not, this is node 1, comma node 1. This is node 1, comma node 1. But here it is not node 1, comma node 1. Here it is a local node number. What is the local node number corresponding to node 1?
node 1 minus 1.
No. No, it's not that way. So it is 0, comma 0, right? So you're taking 1, comma 1. You're finding what is the global node number corresponding to 1, comma 1. How did you do this? See, 1, comma 1. You're looking at this array. In element 2, 1 is 2. So this is node 2. It is. So this is what I'm calling node 1 in the code, and this is actually node 2 in the code. This is actual numbers. These are actual numbers. This is actually this entry, right? So this entry is always 1, comma 1. So this is just k of 0, comma 0, right? So you have to get the logic. I'm taking this matrix. I'm taking the first entry of the matrix, and I'm seeing where this first entry has to go into. So where it has to go into, I'm looking at the connectivity matrix. Yeah, by the way, this matrix of elements is called connectivity matrix. This is called connectivity matrix. I'm seeing where it has to get into, and I'm putting that number here. So this entry, which is 1, comma 1, has to go into node 1, comma node 1, but node 1 is 2. But this node 1 is 2, that the code will automatically do. We don't have to write it every time. So that is the whole point of coding it, right? Suppose we have 1,000 number of elements. We don't need to do this. So node 1, comma node 1 is this. So this since Python numbering starts at 0, I'm putting 0. So now tell me the next few lines. So I'll know if you have understood. What is the next one?
node 1, comma node 2.
So basically, let me write this. All of them are of this format. right? Capital
Yes,
K is
sir.
equal. Yeah. So I'll put this. Now what all I should plug in? So 0, 1, 1, 0,
1, comma 1.
1, 1. Now tell me what I should put here.
Node 1, comma node 2.
Yes. So and here also it's the same. Okay. So here
Node 2,
Node 2,
node
comma
1.
node 1.
so here also it's the same. And here
Node 2, comma node 2.
okay. So this is done. So this is the code. That's it. So as you do it over all elements, it will automatically get assembled. You don't have to do it multiple times. You remember when we did it by hand, we had to do it 2 times. But since you have a loop over it, this will automatically assemble over all the elements. If you have a doubt, you can check. Okay, this is AE doesn't make sense. A star E by L. So this I can compile. This I'll compile. This I'll run. Now this code, let me run. Fine, there's no error. So what should I do? Second step is assemble the global stiffness matrix. I'll uncomment this, right? So K is equal to assemble global stiffness of A. This is a function name. So when you're writing it in a function, so this is a function name. Whenever you call this function name, it has to return. So okay, I made a mistake. So here, this is assemble it, but it will keep it to itself. It has to return it to whatever is calling it, right? So say return K. After assembling, it has to return it to the whatever function, whatever called it. So return K. So this K will take the value of the assembled global stiffness matrix. Now what is F? What is F in our case? We are applying force where? So F is actually a part of the boundary problem definition. What is F? F is the force vector. How many elements it has?
3 elements, 0, F.
Yeah, 0 F1. Let me take the force as 1, right? Because in computer we can only deal with numbers. We cannot put. Yeah, so I'm taking force as 1. Okay. Now let us run up to this point and see if everything is correct. Let me run up to this point and let me print K, right? Print K. K is none. Says K is none. What happened? Hmm. So yeah, there is some problem. So AE is fine. Nodes is fine. LMs is fine. Elements is fine. K return K. So suppose I don't do any assembly, what happens? K is zeros. Let's do one thing. Let us print. So when we get some, let's say print K here and then print K here. And this is not needed. So this I'll comment out. So let us run this now. right? So there it is printing correctly. So here note that there is no print statement here. The function before assembly it is printing 0, 0, 0, and after assembly it is printing 1, -1, 0, -1, 2, -1, -0, -1, 1. So up to this point it is okay, right? Up to this point it is okay. Okay. It has to be returned brackets k. But it's not. It should actually return k. Let's see if it works now. It's print k I can get rid of. And let me turn off. So okay, the problem. Okay, let me do one thing. Run all. That will help. Yeah. Now let us check what k is. Yeah. Now it has the correct value. So for some reason it didn't do it properly. Now it's fine. So k is correct in the problem. So next thing is you have to enforce the boundary condition, right? So this is the third step. Enforce boundary conditions. So what is happening in enforced boundary conditions? You are having it will operate on k, f, and the boundary nodes. So what did we do? We saw when enforcing the boundary nodes, we looked at the boundary nodes array. So boundary nodes are 1 and 3. So 1 and 3 are boundary nodes. And how did we modify the stiffness matrix? The corresponding rows, we made it 0 except that one, right? So you look at the first row of the stiffness matrix. So first row is a boundary row, and in that row you made every entry 0 except the first entry. So what is the logic here? So what should be? How do I enforce the boundary condition here? So okay, what should I do here? You can tell me. So first loop over all boundary nodes. Is that okay? For I in boundary nodes. Yeah. Now tell me what I should do. I have to make the first row 0. So what should I do? Any idea? Hello?
Yes, sir. It's if the entries which are equal, that is m is a of m is equal to n, then it is 1. Otherwise,
Okay.
it is 0.
Okay, so which means I should run over the entries in that also, right? So that's correct. You're right. So instead, let me give you another option. I'll set everything equal to 0 and I'll make this alone 1. Is that also fine? I'll make everything 0 and set this as 1. Instead of checking for every element, both will end result is the same, but this is more shorter, right? The code will be shorter. Instead of writing 2 if conditions and looping over every element, I'll do this rather. So I'll say say k of what is the shortcut for every element I said for all elements in a row. So a row is I, comma colon, right? So then to select the entire row, we say for the entire row it is 0, and I'll say for that row that diagonal entry alone is 1, and the force in the force matrix f of II is equal to 0. Is this okay? This is what we did. We didn't do anything else. So for enforcing the boundary condition, we are sending this array into it. And then we are modifying the array accordingly. So wherever you have a boundary condition, you're setting the displacement equal to 0. So if you want to set the displacement equal to 0, the diagonal entry alone should be 1 and all other entries have to be 0. So initially it will make the entire row 0, then it will override the diagonal entry with 1. That's all. So now you just return. What should you return? K and F. That's why we made the modification, right? Nothing else is required. So return K and F. And you take the K and F here. So Kf is equal to this. So what is the last step? We have to solve for it. So again, I'll run everything and we'll see if the K is correct. Is this okay? This is the K we had, right? So U1 equal to 0. Then the second one is the equation, actual equation. And the last row is U3 equal to 0. Now what is the last step? Solve for U1, U2, U3, right? So 4, solve for U1, U2, U3. How do I solve for? Let me call the solution vector U. Now tell me the code for solving it. How do I solve?
np dot
And
linear
yes,
algebra dot linear algebra dot
solve.
k comma k, k comma f.
Yes, perfect. So remember, so what is the answer we got here? The answer we got is FL by 2 AE. So we should get U2 is equal to 0.5 because F is 1, L is 1, A is 1, E is 1. So we'll do this and let me print U here. Yeah, so U is U1 is 0, U2 is 0.5, U3 is 0. So this is the complete code to solve a problem with bar elements. Yeah, we are way out of time, but yeah, I thought we could get further into the beam elements. So this is a simple problem we are using. We are solving using Python, but it's actually meant for much more complex problem. Suppose you had a truss. Say we had the truss which I just showed. Where is it? Okay, this one. Suppose you had a truss like this. This program is capable of returning the displacements at all points, all the nodal points of the truss. So if you have a 100-member truss, it takes hardly a few seconds to solve for it. So maybe I'll set them as an assignment. So this procedure is exactly the same. Nothing will change. We'll get to the truss problem soon, but yeah. So this is basically it. We can. Yeah, maybe as a homework, I'll give this so that you can practice this. So we couldn't start beams, that's a problem, but it's okay. We'll go do it in the next class. But I just want to make sure everybody understands. So let's have it as an exercise. So the exercise is look at this problem. I'll also post it as an assignment so that you can like directly submit your code and this one in the. Yeah. Now look at this problem, right? So think of this problem. You have the left end fixed. And you have a bar like this. And say you're dividing it into 5 elements. You're dividing it into 5 elements. Sorry, you're dividing it into 5 elements. And you're applying nodal forces like this. So here it is F1. Sorry, Let me call it F2, F3, F4, F5, and F6. Or wait a minute, so this is a node. This is F2, F3, F4, F5, and F6. Now the condition I'm giving you is that this is X, right? So you take everything as the total length, you take it as 1 meter. So each piece will be 0.2 meters. So this is 0.2, 0.2, 0.2, 0.2, 0.2. And suppose this is X. The force at a distance X, I'm giving it as 1 into X, right? Just to make it simple, or make it 5 into X, 5X, say 5X newtons or whatever. So so force at a distance X, we call it as 5X. So if you look at it, what is F2? F2 is a distance of 0.2. So what is F2?
2, sir.
Sorry?
2 newtons, sir.
No, F2 is at a distance of 0.2 from this distance. So
1 Newton, sir.
0.2,
1 Newton.
1. F3 is
2 newtons.
Yeah. So, and F4 is 3, F5 is 4, F6 is 5. So this is the forces. These are the forces. Length is same. Take AE as the same. Take AE as 1. That is AE is equal to 1. E is equal to 1. You can take this. Now solve for the displacements. Right? Solve for the displacements everywhere. So we will see how it goes. So you can use the same code. Anyway, this code is available to you all. I have just edited the same code, right? So this code is available to you. You don't have to assemble anything because this code is already there. All parts of the code is going to work. But I would strongly suggest that you do it again, right? You take a copy of it, delete everything else, and then you can you develop the code by yourself so that it's a practice. And in that code, what you can do is you solve this problem. So you proceed as it is. You give your code. So give your problem input. And finally, you give the vector u, which is u1, u2 up to u6, and report the reactions. What is the reaction at the support? We'll see how you get the reaction at the support. So this I have not taught you, but take it as a challenge, right? It's easy. It's just a one-step thing. You have to use the stiffness matrix only, but you see how the reaction you get. So the reaction, if you guess, it has to be equal to what? It has to be 15 newtons, right? Get the reaction and check if it is 15 newtons. Yeah, so this I'll post it as a assignment in that class group. So make sure you understand this part very clearly so that when we go to beams, the stiffness matrices are different, but the concept is exactly the same. Whether it is a beam or a frame or anything beyond that, concepts are the same. So the code will have the same structure. Nothing will change except the first part, which is the bar stiffness. Instead of bar stiffness, you'll have something called beam stiffness. Then instead of beam stiffness, you'll have a frame stiffness. So have this code as a template. Go work through the code yourself. So the structure, if you see, it is very simple. You have one function to get element stiffness. You have one function to get the global stiffness. Then you enforce the boundary condition, put everything and solve. So individual parts of the code are all like 3 lines or 4 lines, not too hard. So you can solve it. You can submit the homework. It's not going to be graded or anything, but yeah, more regular you are, it will help you further. So maybe we'll also get some feedback from the workshop. Yeah, so work through it. If you have any doubts, you can ask in the next session. So any other doubts now? You have anything else that is not clear?
Clear, sir.
Okay. Yeah, so are there others? If there's any other doubt, or you can put your hands up, you can. Yeah, you can tell me if you have any doubts. And as I said, you will find all the material here. So today's recordings will also be here. Today the code is updated, so you can see the updated code here. Then I think assignment will also come up somewhere here. So if I give you that, you can put it somewhere here. Yeah. So make use of this. We'll see how it goes. So next sessions, we have to talk. We have to discuss, and tentatively we'll have it next weekend. But depending on the availability of people, we have to see.
Okay, sir.
Yeah.
Thank you, sir.
Okay. Thank you. So thanks for attending. Stop
Thank
the
you, sir.
recording here.